The definite integral is going to relate to an area under a curve. And with the definite integral, it's going to be over a specific interval of values that we're looking at. So let's go through some examples here, some with some context, and then kind of ending with one that's a little more abstract. But with these, we'll be able to use geometry in order to calculate, and then we'll get into some more complicated curves where some calculus will come in. So for this first example, suppose a car travels on a straight road at a constant speed of 40 miles per hour for 2 hours, and we can see our graph of the velocity below. So what we can see here is we have flat graph at 40, and then we're looking over the interval from time equals 0 to time equals 2. Now, in terms of the question, how far has it gone? We don't actually need to see the picture because what we have is the fact that distance is equal to rate times time. So we have the rate, we have the amount of time that passed, so we would have 40 times 2, so the distance would be 80, and that would be 80 miles. So we could do this calculation with the graph completely, but what we want to do is connect to the graph because that's where our calculus concepts will come in. So this 80 miles, what we're doing here, so this 40 by 2, so we have this flat line at 40, 2's are cut off. So what we've done here is created a rectangle, and by taking 40 times 2, what we've done is we found the area of this rectangle. So what we have here is, by taking this 40 by 2 rectangle and then calculating the area, we've also found this distance that's been covered. And with that, it's the idea of this cumulative area that was enclosed in this interval from 0 to 2 for this function that's graphing 40 as a straight line. So there's kind of this interval of values for t as well as a function that we're graphing. So the accumulated change is the equivalent to the area under the curve is what we're getting at here, which ties to our definite integral. Something that's also at play here that I just kind of want to introduce the idea of, but we're going to talk about a lot more later on. So our function here, I'm just going to bring through that notation we've used before. So for graphing velocity, it's like we're graphing this function v of t, which something we talked about previously is if we have s of t, then v of t is just the first derivative, and then a of t is the derivative of v of t, and the second derivative of s of t, where s is just a position function. Now the answer we got out here is a distance, so this is actually relating to a function s of t that's mapping distance. So what we did here is we went backwards from what we usually do. We have a function that's velocity, and we took it back to our original s of t. So it's like we started with a derivative function and went backwards. And that movement there is called the antiderivative. So that's something we're going to be doing, and it's what we're getting to with this section, is this idea of an antiderivative, where we start with a derivative function and we want to go back to the original, and how we relate to that is with the area under the curve. So again, just wanted to kind of sneak that in there, but we'll talk more about that later. Okay, so let's say it wasn't traveling the same speed the whole time. Let's say it was steadily increasing from 0 to 40 miles per hour over the 2 hours. So with this one, we're still looking from 0 to 2, but now we're getting more of a triangle out because it's this straight line as increasing from 0 to 40. So what we want to do is, this is it's not as straightforward as just taking that distance equals rate times time, because it isn't a constant speed, it's changing. So with this, we definitely need the graph so we can see how it's changing. So what we learned from that last one is we just need this area under the curve. So what we have here is a base that's a distance of 2, the height is 40, and it's a triangle. So what we need is the distance here. Distance is going to equal 1/2 times base times height, which is going to be 40. So with this one, they traveled 40 miles in total with that increasing speed over those 2 hours. Okay, and then let's talk about this case here. So we just want to find the area under the curve here, no context of a word problem. So our function is y equals negative x over 2 plus 5. I'm just going to rewrite that a little bit to be negative 1/2 x plus 5 so I can see my slope and intercept a little bit easily. And the interval is from -5 to -1. Okay, so let's start by graphing our function. So this has a y-intercept at positive 5, and then a slope of -1/2. So I'm just graphing my linear function here. And connect that with a straight line. Okay, then what I want to do is find my interval. So we're looking from -5 to -1. So -5 cuts off right here. -1 is right here. So there's a few ways to go about this. I'm trying to decide which one I want to do. We could do a trapezoid calculation. That would absolutely work here. Or if you want to kind of divide it up, that would be fine too. Like it's coming from a triangle plus a rectangle. That would work too. I'm gonna go with the separated rectangle and triangle. Might be a little bit more work, but let's just go for it. So I have this 4 by 1, 2, 3, 4, 5.5 rectangle. So that'll take care of the area of the rectangle. So I'm going 4 times 5.5. And then I'm going to add on this triangle, which has a base of 4. So I'm going 1/2 times 4. And then the height is going to be 2. So 4 times 5.5 is a 22. And then plus 4. So what we have here is a total of 26. We could also do here is just like count the number of squares we have there. But in terms of this, 26 will be perfect. So all of this is to get at the idea of area under the curve, how it comes through in word problems, and just how we would find it with a given function. But what we'll do in the next section is, in terms of more complicated functions, how can we estimate it?